Hi, my name is Andrea Munroe. I'm from Indiana Wesleyan University, and I worked this summer with the MONA collaboration on the nonlinear behavior of our plastic scintillator neutron detectors. So MONA stands for the Modular Neutron Array. The MONA collaboration, of course, works with this MONA array. MONA has 144 plastic scintillator detectors total. Each of them is 2 meters long and 10 centimeters by 10 centimeters wide and high. And then each end of each bar has a photomultiplier tube. So we've used these bars for many years in analog electronics, but we've not yet used it for digital. And we're looking forward to using digital in our new detectors, but we want to know how our detectors work with them first. So we sent some of these detectors to the Los Alamos National Lab and did an experiment with them. But when we looked at the position data, which we find from calculating from the time difference between the two photomultiplier tubes, we found that our digital position spectrum has an anomalous shape. So you can see here, this is our analog spectrum in red, and then below it is our new digital spectrum in blue. The way that we decided to test this light propagation behavior was to take one of these MONA bars and then several CMDA bars. These are cosmic muon detection array bars, and they're the exact same except they're half size. And we drew triplet coincidences between these and the MONA bar. So we had one on top and one on bottom. And then when we had cosmic muon data that went through all three, we knew the actual position of this event on these bars. So then we could draw a map from the time difference, which gives us our position, and the actual position on the bar. So we can compare our digital and physical positions. So once we had this data, I made a graph that has the actual position versus the calculated position based on this time difference to make our mapping between the two. And you can see that in this middle section here, it is very linear until about the end 40 centimeters of the bar. And then at these end 40 centimeters of the bar, it does deviate. It doesn't show as well on this graph because it is very zoomed out. But if you look closer, this is a matter of several centimeters, up till 6 to 8, which is very significant. This shows how nonlinear our detectors are in this portion of the bar. So with this data, we decided to look at the waveform shape analysis of the actual light in these phototubes to figure out why it was giving us this nonlinear behavior. So to start out, we saw that we had a rise time of around 4 nanoseconds for events that happened near the phototube, but when events happened farther from the phototube, the rise time rose to about 5 nanoseconds. You can see that we made a scan across the entire bar comparing these rise times, and that it is linear all the way through until this last 40 centimeters on either side, where it becomes nonlinear once more and rises to 5 nanoseconds rise time. We also did a similar analysis of pulse shapes, and we can see that they are consistent through the very center of the bar up until the final 40 centimeters when it does deviate once more. From this waveform shape data, we are able to conclude that the cause of our nonlinearity was reflection in our bars. We know that when we go from a larger scintillator bar into a smaller photomultiplier tube with a taper, that some of that light, by Liouville's theorem, has to reflect off of the taper and back into the bar. This is this light that we're detecting on the opposite phototube of the other side of the bar. We know that this always has to happen when we have a mismatch between the areas of the photomultiplier tube and the scintillator bar. Looking forward, we know that our next set of scintillator bars will not suffer from this reflection, thus it will not be nonlinear. But for the data we've already taken with digital acquisition, we know that we can correct for it still in 2 different ways. The first is that we just use the data in the center of the bar because we have already shown that this is nonlinear. The second is to apply a position correction algorithm to our data. I created 2 example correction algorithms over the summer. The first is shown here on the left, and this is from the data that we took from mapping the nonlinearity. The second is a reverse engineered shape matching algorithm where I took the intended spectrum and compared it to the spectrum that we got, and I corrected it in this way. Our focus, however, is on the next generation of bars that we will be creating for neutron detection. We know that we want to have a cross-sectional area match between the scintillator bar and the photomultiplier tube because of Liouville's theorem, and because we know that if they do match, we will no longer have this reflection off the end of the photomultiplier tube into the opposite photomultiplier tube. In this case, we would no longer have the nonlinear behavior caused from this reflection, and then all of our position spectra will be accurate.